Welcome to our lecture on jet streams. Today, we are going to explore the fascinating high-altitude winds that circle our globe, shaping weather patterns and driving atmospheric circulation.
Let's start by defining what jet streams actually are. They are narrow, concentrated bands of air flowing in the upper troposphere. They are circumpolar, meaning they circle the Earth with the poles as their centers. Because the air is directed toward the axis of the stream, they are quite narrow, typically just 50 to 150 kilometers across. They flow from west to east, making them westerlies, and operate as geostrophic streams at very high velocities, often following a wavy, meandering path.
How do these powerful winds form? The primary drivers are pressure differences between large bodies of air, known as air masses, combined with the rotation of the Earth. When air masses with different temperatures and moisture levels meet, they create a pressure gradient. As air moves to balance this pressure, the Earth's rotation applies the Coriolis force, steering the winds into concentrated streams.
To understand jet streams, we must understand geostrophic wind. About 2 to 3 kilometers above the surface, winds are free from the friction of the ground. When atmospheric pressure lines, or isobars, are straight, the pressure gradient force pushing air from high to low pressure is perfectly balanced by the Coriolis force pulling it in the opposite direction. The resulting wind blows parallel to the isobars. This is known as a geostrophic wind.
You might wonder why winds don't just flow directly from the high pressure of the tropics to the low pressure of the poles in the upper atmosphere. Because these upper winds are geotropic and experience very little friction, they are subjected to a strong Coriolis force. This force deflects them so much that instead of one massive circulation cell from equator to pole, the flow breaks down into 3 distinct smaller cells: the Hadley, Ferrel, and polar cells.
Jet streams are essentially produced by winds flowing from the tropics toward the poles, just below the tropopause. Both hemispheres have them, though the northern ones are stronger due to greater temperature contrasts. The jet stream that forms between the polar and temperate air masses is the polar jet. The one between the temperate and tropical air masses is the subtropical jet.
Why do we call them westerlies? In the upper troposphere, air flows from the warmer, less dense regions near the equator toward the colder poles. As this air moves poleward, the Coriolis effect deflects it. Anything moving toward the poles deflects to its right in the northern hemisphere and to its left in the southern hemisphere. This consistent deflection turns the poleward flow into a west to east flow in both hemispheres.
These two main jet streams flow at different altitudes. The subtropical jet stream flows much higher, between 10 and 16 kilometers above the ground, while the polar jet stream flows lower, between 6 and 9 kilometers. This altitude difference exists because the troposphere itself is thicker at the equator, reaching up to 18 kilometers, and thinner at the poles, where it is only about 8 to 9 kilometers deep. Jet streams are incredibly fast thanks to the low friction in the thin upper air. The velocity is determined by the temperature contrast between the colliding air masses. A greater temperature difference means a faster jet stream. Because the temperature contrast is higher in winter, the average speed is around 120 kilometers per hour, compared to 50 in the summer. At their very core, speeds can even exceed 400 kilometers per hour. The path a jet stream takes is also dictated by temperature. When the temperature contrast between air masses is at its maximum, the jet stream is strong and flows in a nearly straight west to east path. However, when the temperature contrast drops, the jet stream weakens and begins to meander, flowing in a wavy, irregular pattern that wanders towards the poles and the equator. These massive meandering patterns in the atmosphere are called Rossby waves. As the jet stream undulates, polar air dips toward the equator and tropical air surges toward the poles. A wave pointing toward the poles is called a ridge, while a wave dipping toward the equator is a trough. These waves are crucial because they help explain the formation of low-pressure cyclones and high-pressure anticyclones. Now, let's categorize these winds. The polar jet and the subtropical jet are considered permanent jet streams. This means they breeze through the upper troposphere for the vast majority of the year, acting as constant fixtures in our global atmospheric circulation. Looking closer at the subtropical jet stream, or STJ, we find it is nearly continuous in both hemispheres during winter. In the southern hemisphere, it persists all year round. However, in the northern hemisphere, it migrates north during the summer and becomes intermittent. The STJ is highly significant because it is closely connected to the behavior of the Indian and African summer monsoons. The polar front jet, or PFJ, is the strongest of the jet streams, though its position is highly variable. In the summer, it shifts toward the poles, and in the winter, it moves toward the equator, becoming very strong and continuous. It plays a massive role in shaping the climate of regions around 60 degrees latitude and dictates the path, speed, and intensity of temperate cyclones. Aside from the permanent jets, there are temporary jet streams that only appear during specific seasons. Unlike the high-altitude permanent jets, these are major high-velocity winds located in the lower troposphere, earning them the name low-level jets. The two most important ones are the Somali jet and the tropical easterly jet. The Somali jet is a southwesterly low-level jet that occurs during the summer months. It flows over northern Madagascar and off the coast of Somalia. Peaking in intensity from June to August, this jet remains relatively steady through September and plays a critical role in driving moisture toward the Indian subcontinent, heavily influencing the Indian monsoons. The tropical easterly jet, or TEACH, is a dominant feature of the Northern Hemisphere summer over southern Asia and northern Africa. Found between 5 and 20 degrees north latitude, it persists from June to early October. During the South Asian monsoon, the TEJ induces secondary circulations that enhance convection, essentially acting as an upper-level exhaust system that pulls the strong southwest monsoon forward. While the exact mechanics of the TEJ are still being studied, it is widely believed to be powered by the uniquely high temperatures over the elevated Tibetan Plateau during summer. Interestingly, in recent years, the temperature contrast between the Indian subcontinent and the surrounding ocean has decreased. Consequently, the TEJ has shown a weakening trend, which is a concerning sign for the vitality of the Indian monsoons. Zooming out, how do jet streams impact global weather? Primarily, they help maintain the Earth's latitudinal heat balance by facilitating a massive exchange of air between the equator and the poles. By steering massive air masses, their movements, or lack thereof, can lead to extreme weather events, including prolonged heat waves, severe droughts, or devastating floods. In temperate regions, jet streams act as the ultimate weather makers. They push air masses around, moving weather systems to new areas or causing them to stall. The polar front jet is especially crucial here, as it acts as the boundary separating cold polar air from warmer mid-latitude air. This boundary is the birthplace of frontal precipitation and powerful frontal cyclones. The polar front jet drives temperate weather through phenomena known as troughing and ridging. Ridges occur when high-pressure warm air pushes northward against cold air, generally bringing quiet, settled weather beneath them. Conversely, troughs occur where lower-pressure cold air drops southward into warm air. The area ahead of a trough is highly unstable, leading to active stormy weather. Within these ridges and troughs, we find localized areas of intense wind called jet streaks. When winds exit a trough, they spread out or diverge. This creates a void in the upper atmosphere, causing air from the surface to rush upward, creating a low-pressure system and cyclonic storms. Conversely, when winds converge entering a streak, air piles up and sinks, creating high pressure at the surface and clear anticyclonic weather. This brings us to the polar vortex. The polar vortex is a massive, cold, cyclonic parcel of air in the upper troposphere that can stretch up to 2,000 kilometers wide. It sits over the polar regions primarily during winter. Unlike seasonal cyclones, polar cyclones can form at any time, sometimes in less than 24 hours, and their movements are notoriously difficult to predict. Normally, a strong polar jet stream acts like a fence, keeping the polar vortex locked in place over the Arctic. However, when the polar vortex weakens, the jet stream buckles. This allows the vortex to intrude deep into mid-latitude regions. This buckling of the general wind flow is what causes severe polar vortex cold waves, delivering dangerous sub-zero temperatures to places like the United States and Canada. Let's break down exactly how the polar vortex slips southward. It starts when the temperature contrast between polar and temperate regions drops. This causes the polar jet to weaken and meander, forming deep Rossby waves. These meanders create alternating high and low pressure cells. If the meandering is severe, the high pressure cells push northward, physically displacing the polar cyclone and forcing it to slip down into temperate regions. On the opposite end of the temperature spectrum, we have heat domes. A heat dome occurs when Rossby waves trap a high pressure zone in place for an extended period. The air inside this dome continuously sinks toward the ground. As it sinks, it compresses, which causes it to heat up dramatically. This phenomenon is responsible for record-shattering temperatures, violent thunderstorms, and explosive wildfires. Heat domes often create atmospheric traffic jams known as blocking patterns, which completely halt the normal west-to-east movement of weather.
A famous example is the Omega block. Named because the jet stream's path resembles the Greek letter omega, it features a massive high-pressure heat dome anchored in the middle, flanked and locked in place by two stubborn low-pressure zones on its east and west sides. Beyond weather, jet streams have a massive impact on global aviation. Commercial airlines carefully plan their routes around these high-altitude rivers of air. When flying east, pilots will intentionally route their aircraft into the jet stream to catch a massive tailwind, saving time and fuel. Conversely, when flying west, they will chart paths to actively avoid flying directly into these 200-kilometer-per-hour headwinds. However, utilizing jet streams comes with hazards. The sheer speed and shear of these winds can cause clear air turbulence, creating suddenly bumpy flights, even when the sky looks perfectly calm and cloudless. Furthermore, during volcanic eruptions, dangerous plumes of volcanic ash can be sucked directly into the jet streams, creating severe hazards for the very flight paths that airlines rely on. These atmospheric dynamics set the stage for complex weather systems across the globe. Moving right into the next major atmospheric phenomenon, let's examine temperate cyclones. These are cyclonic systems that develop in the mid and high latitudes, specifically between 35 and 65 degrees in both the northern and southern hemispheres. Because of their location and how they form, you might also hear them referred to as mid-latitude cyclones, extratropical cyclones, frontal cyclones, or wave cyclones. To truly grasp how these systems work, we have to contrast them with tropical cyclones. While tropical cyclones have a thermal origin driven by convective cyclogenesis, essentially heat rising from warm oceans, temperate cyclones have a dynamic origin. They are driven by frontal cyclogenesis, which is a complex physical interaction of different air masses, heavily influenced by the Coriolis force. Since temperate cyclones are driven by the interaction of air masses, we first need to define what an air mass actually is. An air mass is a massive body of air that has very little horizontal variation in temperature and moisture. These are not small, localized breezes. They are an integral part of the planetary wind system, extending all the way from the Earth's surface up to the lower stratosphere, and they can span across thousands of kilometers. An air mass doesn't just form anywhere. It requires a source region. When a large parcel of air remains over a homogeneous, uniform area for a sufficiently long time, it actually acquires the characteristics of that area. These homogeneous regions, which can be vast ocean surfaces or massive plains and plateaus, establish a heat and moisture equilibrium with the air above them. Looking at the globe, the main source regions are located in the high-pressure belts in the subtropics, which give rise to tropical air masses, and around the poles, which are the source for polar air masses. When an air mass eventually moves away from its source region, its upper level maintains these physical characteristics for a long period because the air is stable and stagnant, meaning conduction and radiation aren't very effective at changing its core properties quickly. For a source region to effectively shape an air mass, it needs specific ideal conditions. The area must be extensive with gentle divergent air circulation, specifically gentle anticyclonic circulation. High-pressure areas with very little pressure gradient are perfect for this. Notice that there are no major source regions in the mid-latitudes. The air there is simply too chaotic, constantly disrupted by frontal cyclones and other disturbances. Based on these ideal conditions, meteorologists identify 5 major source regions on Earth. These include the warm tropical and subtropical oceans, the subtropical hot deserts, the relatively cold high-latitude oceans, the very cold snow-covered continents in the high latitudes, and finally, the permanently ice-covered continents in the Arctic and Antarctica. To easily identify the air masses that form in these regions, we use a simple 2-letter naming convention. The first lowercase letter describes the moisture properties. C stands for continental, meaning the air is dry, and M stands for maritime, meaning the air is moist. The second uppercase letter describes the temperature of the source region. T for tropical and warm, P for polar and cool, and A for Arctic or Antarctic, which is extremely cold. Beyond the naming convention, we also classify air masses by how their temperature compares to the ground they travel over. A cold air mass is simply one that is colder than the underlying surface. Major cold source regions include the Arctic Ocean and the Southern Ocean, which produce cold and moist air, as well as Siberia and northern Canada, which produce cold and dry air. Conversely, a warm air mass is one that is warmer than the surface it is traveling over. The primary warm source regions are the Sahara Desert, which generates intensely warm and dry air, and the vast tropical oceans, which generate warm and highly moist air masses. Let's break down the specific types of air masses, starting with continental polar, or CP. They originate over the Arctic Basin, northern North America, Eurasia, and Antarctica. They are characterized by dry, cold, and stable conditions. In the winter, they bring frigid, clear weather. During the summer, as the land masses warm up and snow melts, these air masses become slightly less stable. Next, we have maritime polar, or MP, air masses, originating over oceans between 40 and 60 degrees latitude. Interestingly, these are often continental polar air masses that have moved over warmer oceans, heated up, and collected moisture. As a result, they are cool, moist, and unstable. In winter, they bring high humidity, overcast skies, fog, and precipitation. But in summer, they tend to bring clear, fair, and stable weather. Moving closer to the equator, we find continental tropical, or CT, air masses. These form over the tropical and subtropical deserts of the Sahara, West Asia, and Australia. They are intensely dry, hot, and stable. A unique feature of CT air masses is that they generally do not extend far beyond their source regions, remaining dry throughout the entire year. Over the warm ocean waters of the Mexican Gulf, the Pacific, and the Atlantic, we find maritime tropical, or MT, air masses. Because they form over warm water, they are warm, highly humid, and unstable. In winter, they cause mild temperatures with overcast skies and fog. In summer, they are responsible for sweltering high temperatures, high humidity, towering cumulus clouds, and heavy convectional rainfall. These massive bodies of air are the primary engines of our global climate system. The properties that influence the weather they bring are their vertical temperature distribution, which dictates stability, and their moisture content. By moving across the globe, air masses transport atmospheric moisture from the oceans to the continents, and they transport latent heat, which is absolutely crucial for maintaining the Earth's latitudinal heat balance. But the most dramatic weather events don't happen in the middle of an air mass. They happen at the edges. Most migratory atmospheric disturbances, such as cyclones and severe storms, originate at the contact zone between two different air masses. The characteristics of the colliding air masses determine the severity of the weather. These highly volatile contact zones are called fronts, which leads us directly into the mechanics of how fronts operate. Moving forward with our discussion on atmospheric dynamics, we now turn our attention to fronts. Fronts are the typical features of mid-latitude weather, specifically in the temperate regions between 30 and 65 degrees north and south. You will find that they are quite uncommon in tropical and polar regions. Understanding how these fronts form and the different types that exist is absolutely essential to understanding the formation of mid-latitude cyclones and the dominant weather patterns in these regions. So, what exactly is a front? A front is a three-dimensional boundary zone formed between two converging air masses that possess different physical properties, such as temperature, humidity, and density. Now, you might wonder why these two air masses don't just mix together. They don't merge readily due to the effect of the converging atmospheric circulation. Their differing physical properties, a relatively low diffusion coefficient, and low thermal conductivity. The life cycle of a front involves two main processes. The formation of a front is known as frontogenesis. You can think of this as a war between two distinct air masses converging on one another. This process may eventually give rise to temperate cyclones. On the other hand, the dissipation of a front is known as frontolysis. This occurs when one air mass effectively wins the battle by overriding the other, causing the frontal boundary to break down. The direction in which this convergence, or frontogenesis, happens depends on where you are on the globe. In the northern hemisphere, the convergence of air masses happens in an anti-clockwise direction. Conversely, in the southern hemisphere, it happens in a clockwise direction. This rotational difference is entirely due to the influence of the Coriolis force acting on the moving air masses. Let's look at some general characteristics of fronts, starting with their thickness. The temperature contrast between the two air masses influences the thickness of the frontal zone in an inversely proportional manner. This means that if you have two air masses with a very high temperature difference, they are highly resistant to merging. As a result, the front that forms between them is sharply defined and less thick. Frontal activity is almost invariably associated with cloudiness and precipitation. This happens because the warmer, lighter air is forced to ascend. As this warm air rises, it cools down adiabatically. The moisture within it condenses, and this causes rainfall. The actual intensity of this precipitation depends on two main factors: how steep the slope of the ascent is, and the amount of water vapor present in that ascending warm air. Another key characteristic is that a front experiences a wind shift. This is because wind motion is a function of the pressure gradient and the Coriolis force, both of which change across the frontal boundary. Meteorologically, a wind shift is specifically defined as a change in wind direction of 45 degrees or more, occurring in less than 15 minutes, with sustained wind speeds of 10 knots or more throughout the shift. Based on the mechanism of frontogenesis and the associated weather, we classify fronts into 4 distinct types. On weather maps, these are represented by specific symbols, occluded front, with alternating symbols on the same side. Let's examine each of these in detail. First is the stationary front. This occurs when the surface position of a front does not change. Essentially, the two air masses are unable to push against each other effectively. It's a draw. The wind motion on both sides of the front tends to flow parallel to the front, rather than across it. Because the warm or cold front stops moving, we call it stationary. If this boundary eventually resumes its forward motion, it will become either a warm or cold front. The weather along a stationary front can be quite impactful. Even though the front isn't moving across the ground, warm air is still overrunning, or uplifting, along the boundary. This causes cumulonimbus clouds to form, leading to frontal precipitation. Because the front is stationary, frontal cyclones migrating along it can dump heavy amounts of precipitation over the same area for extended periods, which often results in significant flooding. Next, we have the cold front. A cold front is formed when a cold air mass advances and replaces a warm air mass, or when a warm air mass retreats and the cold air advances. In this scenario, the cold air mass is the clear winner. Because cold air is dense, it bulldozes under the warm air, creating a steep-sloped transition zone. The front eventually dissipates, or undergoes frontolysis, when the warm air mass is completely uplifted off the ground by the cold air. Because of that steep slope, the weather along a cold front is concentrated in a narrow band of cloudiness and precipitation. The upliftment of air is quite rapid, making the weather along it violent. A cold front moves up to twice as quickly as a warm front, producing sharper changes in weather over a shorter duration. During summer, severe storms, thunderstorms, and even tornadoes can occur in the warm sector. As the front passes, temperatures can plummet by more than 15 degrees within just the first hour. You can actually watch a cold front approach by observing the clouds. Its approach is marked by increased wind activity in the warm sector and the appearance of high cirrus clouds. As the front gets closer, these are followed by lower, denser altocumulus and altostratus clouds. Right at the actual front, where the aggressive uplift happens, you will see dark nimbus and towering cumulonimbus clouds, which are responsible for the heavy showers. Now let's look at the warm front. A warm front features a gently sloping frontal surface, along which warm air actively moves over cold air. Here, the warm air mass is trying to advance, but it's too weak to completely scour out the dense cold air mass at the surface, so it rides up over it instead. The passage of a warm front is marked by a rise in both temperature and pressure. Frontolysis begins when the warm air mass completely sits over the cold air mass on the ground. The weather along a warm front is quite different from a cold front. As the warm air moves up that gentle slope, it condenses and causes precipitation. However, because the slope is gentle, the changes in temperature and wind direction are gradual. Instead of violent storms, warm fronts typically cause moderate to gentle precipitation that spreads out over a very large area and can last for several hours. The cloud formation along a warm front also follows a specific hierarchy. Far ahead of the surface front, you will see high cirrus clouds, followed by cirrostratus, then altostratus, and finally nimbus clouds closer to the front. Because the gradient is so gentle, the air isn't forced up rapidly enough to form towering cumulonimbus clouds. Interestingly, the ice crystals in the high cirrus and cirrostratus clouds ahead of the front often create a visible halo around the sun or moon. The fourth type is the occluded front. Occlusion is a process where the faster-moving cold front of a rotating low-pressure system actually catches up with the slower warm front. When this happens, the warm air mass is overtaken, and the cold air goes underneath it, forcing the warm air entirely upwards off the ground. Frontolysis begins when the warm sector diminishes completely at the surface, leaving a long occluded front. Because an occluded front is essentially a collision of fronts, the weather along it is highly complex. It produces a mixture of both cold front type and warm front type weather. You will see a combination of the cloud types we just discussed forming on opposite sides of the occlusion. This occlusion process is a critical stage in the life cycle and formation of mid-latitude cyclones. To summarize these interactions, think of them as a contest. A stationary front is a tie with no clear winner. In a cold front, the cold air mass is the clear winner, completely overriding the warm air. In a warm front, the warm air tries to advance but fails to beat the dense cold air. And an occluded front is a double victory for the cold air mass. Note that cold, warm, and occluded fronts are all excellent examples of temperature inversion, where warmer air is forced above cooler air. This sets the stage perfectly for understanding the origin and development of temperate cyclones, which we will explore next.
Let's dive right into the origin and development of temperate cyclones. A key distinguishing feature here is that the isobars in a temperate cyclone are not closed. If we look at how weather manifests within these systems, we see distinct patterns based on the fronts. For instance, heavy, torrential, short-duration rainfall accompanied by thunderstorms is typically witnessed along the rapidly moving cold front. This intense weather is due to the rapid uplift of air, which leads to the formation of towering cumulonimbus clouds.
To understand how these cyclones form, we rely on the polar front theory. According to this theory, temperate cyclones are born when two very different air masses meet: warm, humid air masses traveling from the tropics and dry, cold air masses moving down from the poles. When they collide, they don't just mix easily. Instead, they form a boundary called a polar front, which is a surface of discontinuity. You will generally find these conditions occurring over subtropical high-pressure belts, subpolar low-pressure belts, and high up along the tropopaths.
Let us look at the circulation dynamics, specifically in the northern hemisphere. Here you have warm air blowing from the south and cold air coming from the north of the front. As the atmospheric pressure begins to drop along this frontal boundary, the warm air pushes northwards and the cold air pushes southwards. Because of the Earth's rotation, the Coriolis force acts on these moving air masses, setting up a distinct anti-clockwise cyclonic circulation. As the cyclone develops, the warm air, being lighter, glides up and over the heavier cold air. This creates a sequence of clouds ahead of the warm front, leading to precipitation. Meanwhile, the cold front approaches from behind, aggressively pushing the warm air upward, which triggers the development of cumulus clouds. Because the cold front moves faster, it eventually catches up to and overtakes the warm front. The wedge of warm air gets completely lifted off the ground, a process called frontolysis. At this point, the front is occluded, and the cyclone loses its energy source and dissipates. When and where do these temperate cyclones happen? Seasonally, they are most frequent in winter, late autumn, and spring, bringing rainstorms and cloudy weather. In the summer, their paths shift much further north. Geographically, they have a wide distribution. They sweep across the USA and Canada, particularly over the Rockies and Great Lakes. Another major belt extends from Iceland across to Russia and Siberia. We also see them over the Baltic Sea, the Antarctic frontal zone, and very importantly, originating in the Mediterranean basin and traveling all the way to India during winter, where they are known as western disturbances. Moving on to their physical characteristics, temperate cyclones are massive. They are asymmetrical and generally shaped like an inverted V. They typically stretch across 500 to 600 kilometers, but over vast landmasses like North America, they can spread over 2,500 kilometers. Vertically, they reach heights of 8 to 11 kilometers. Structurally, because of how the air masses push against each other and rotate, the northwestern sector forms the cold sector, while the northeastern sector forms the warm sector. How do these massive systems move? An individual frontal cyclone usually lives for about 3 to 10 days. They generally travel from west to east, carried by the prevailing westerlies, with their precise path controlled by the polar jet stream high in the troposphere. If the storm front is oriented east-west, it moves swiftly east. If it points north, it moves north, but usually dissipates quickly as pressure differences drop. However, if the front is directed southwards, it can dip deep into regions like the Mediterranean, creating those crucial western disturbances that bring winter rains to Punjab and Haryana in India. If you are standing on the ground as a temperate cyclone passes over, you will experience a very specific sequence of weather. First, as it approaches, the temperature drops, winds shift, and you might see a halo around the sun or moon through thin cirrus clouds. Then, a light drizzle begins, turning into a heavy downpour as the warm front arrives, which also stops the temperature from falling. Once you are in the warm sector, the rain stops and the sky clears. But don't be fooled. When the cold front finally hits, the temperature drops sharply again, bringing heavy clouds, rain, and thunderstorms. Afterward, clear weather returns, often accompanied by high-pressure anticyclones. It is also important to understand the broader impact of these air masses, a topic that has appeared in UPSC mains. The movement of these massive bodies of air causes macroclimatic changes. For example, they can drag freezing polar air down to cause unusual cold waves in the tropics and subtropics, or push warm tropical air up to cause heat waves in temperate regions. These large-scale temperature anomalies are primarily driven by meandering jet streams known as Rossby waves, as well as the continuous process of moving fronts and frontogenesis.
Now let's comprehensively compare tropical and temperate cyclones, starting with their origin. Tropical cyclones are thermal, driven by heat, whereas temperate cyclones are dynamic, driven by the movement of air masses and frontogenesis. Geographically, tropical cyclones form near the equator, between 10 and 30 degrees latitude, while temperate cyclones form further toward the poles, between 35 and 65 degrees. Tropical cyclones have no frontal system at all, whereas fronts are the very reason temperate cyclones exist. Finally, tropical cyclones only form over warm ocean waters and die over land, but temperate cyclones can form and sustain themselves over both land and sea.
Looking at seasonality and size, tropical cyclones are highly seasonal, peaking in late summer. Temperate cyclones are more irregular, but heavily favor the winter months. In terms of sheer size, temperate cyclones are much larger, spanning up to 2,000 kilometers, compared to the 500-kilometer maximum of a typical tropical cyclone. Shape-wise, tropical storms are elliptical, while temperate ones look like an inverted V. The rainfall patterns differ drastically too. Tropical cyclones dump heavy rain very quickly, whereas temperate cyclones produce slower, steady rainfall that can last for days or even weeks.
When it comes to destructive power, tropical cyclones have much higher wind velocities, ranging from 100 to 250 kilometers per hour, causing severe damage through winds and storm surges. Temperate cyclones have milder winds, and their damage usually comes from prolonged flooding. If you look at a weather map, the isobars of a tropical cyclone are tight, complete circles, indicating a steep pressure gradient, while temperate isobars are V-shaped, with a gentler gradient. Tropical cyclones are short-lived, usually lasting less than a week, and travel east to west. Temperate cyclones can last up to 3 weeks and travel west to east, carried by the westerlies. Internally, these storms operate very differently. A tropical cyclone has an equal temperature distribution at its center and features a calm, rain-free eye. A temperate cyclone has different temperatures in every sector and lacks any calm region. It is active everywhere. The engine driving a tropical cyclone is the latent heat released by condensation, influenced and steered by upper-level jet streams, whereas the relationship between jet streams and tropical cyclones is much less direct. Finally, let's look at clouds, impacts, and prediction. Tropical cyclones feature fewer cloud varieties, mainly massive cumulonimbus clouds, while temperate cyclones showcase a wide variety of clouds at different altitudes. Tropical cyclones operate alone, but temperate cyclones are usually sandwiched between high-pressure anticyclones. In India, tropical cyclones primarily batter the east coast, whereas temperate cyclones arrive as western disturbances, bringing vital winter rain to the northwest. Because of their erratic nature, tropical cyclones are notoriously difficult to predict, whereas the steady westerly path and clear frontal systems of temperate cyclones make them much easier to forecast. To wrap up our discussion, remember these key points. Temperate cyclones are fundamentally dynamic, born from the clash of warm and cold air masses through frontogenesis. They march predictably from west to east, steered by the polar jet stream. As they pass over an area, they bring a very specific sequence of weather, from light drizzles to thunderstorms, driven by their warm and cold fronts. And most importantly, they are entirely different beasts compared to tropical cyclones, varying wildly in how they form, how long they last, and the kind of weather they bring to regions like India.